Welcome to the Newton tutorial series. I'm Mike Cruz with Ac-Tek, and in this tutorial I'm going to be showing you how to generate material for your Newton simulation. More specifically, I'm going to be talking about the material generation and location and separation sections on the generation page. The initial properties, distribution, and other sections I'm going to leave to the next tutorial because they're a little more complicated. To access the generation page, you click on the material generator button on the main button bar right here. On the left hand side you'll see the input and the output grids, and on the right hand side there will be a preview of the geometry as well as your material when you generate some. So let's go ahead and create a belt here, say 1200 millimeters and 3 meters per second. Now along the top we have 5 separate generation points, and each of these generation points can be configured to have different properties, different variables. You could have each of these could have different densities, different material sets, different tonnages, different generation times. All of it can be manipulated between these. Now most users are only going to need 1 or maybe 2 generation points, but we have 5 available if you need them. So an example of where you might use more than one is right here in this dual chute system. You can see from a side view we have 2 feed belts that feed into the same chute. So each of these belts has its own generation point, and they might have different tonnages and different particle sets as well. So when you generate your material under each generation point, the first thing you'll do is you'll specify which particle set you want to use. And these particle sets are taken directly from your particle library. It's the exact same list. So let's pick say a 40 to 100 set. Now down on the main page we have a couple of different settings. There's the bulk density, which is just the bulk density of your material. 830 for coal, or 1600 for copper ore, or 24 to 2700 if you're doing iron ore, depending on your material properties. We'll just set that at 830 for coal. Beneath that is the generation method. Now we have 4 different generation methods. The main one that you'll be using most of the time is layer. And what that means is it's going to generate the material as a sequence of layers that are dropped one after the next, and that's how the material enters the simulation. Alternatively, you could drop just a single block of material at the specified volume, and then it would just it would be a big rectangular block that just all drops into the simulation at the same time. If you generate by clusters or by particles, basically that's saying, well, we're still going to have a tonnage because we're dropping in layers, but now you specify, well, how many clusters do I want to generate, or how many particles do I want to generate? So let's go back to our layer generation method. Now the tonnage obviously is just the tonnage of the material that you want to generate in metric tons per hour. So we'll say 1,000 tons per hour. The generation start time is when do you want to start generating the material. And the generation time is how long do you want to generate the material. So we'll set our generation time at 0 and the start time at 0 and the generation time at, say, 20 seconds, 30 seconds. The acceleration and deceleration period, these control how we generate the material, how we change the tonnage. By default you can leave them blank and it will just generate the full tonnage for the entire generation time. But if you want, like say you were accelerating your belt from a stop or during startup, you could specify an acceleration period. So if we were to say an acceleration period of 10 seconds, what that means is that starting at generation start time, starting at time 0, we're going to linearly increase the tonnage from 0 to whatever the max tonnage right here is, from 0 to 1,000. And that's going to happen over 10 seconds. So by time 10, we're going to be at full tonnage. And for the rest of the generation time, the last 20 seconds, we're going to keep generating at full tonnage. Alternatively, you could put a deceleration period in there, which is just the opposite. So if we set a deceleration period of 15 seconds, what that means is that, at the generation start time, we're going to start out generating our material at full tonnage. And then as soon as we get to the last 15 seconds of the generation time, so that would be 30 minus 15, so it happens to be exactly at 15, we would start decelerating that tonnage. We would decrease that tonnage linearly from 1,000 to 0. So if the generation start time was 60, or the generation time was 60, this would happen at 45 seconds. At 45 seconds, we'd start decelerating from 1,000, and we'd reach 0 right at the last drop, right at 60 seconds. You can't use both acceleration and deceleration together. You can only use one or the other. If you put inputs in both boxes, then it will use the acceleration period and it will just totally ignore the deceleration. So, the location and separation. This is where you specify where do I want to generate this material and what shape do I want to use. So the most common way to do it is by just selecting whichever belt you want to generate it on. So because I created this belt right here under belt 1, 2, or 3, this happens to be belt 1, I can simply say, hey, you know what? I want to generate my material right on belt 1, and then it doesn't give me the option to set the size and position because it automatically says, oh, that's going to be right here in this Dropbox. So if I hit generate, well, to save time, we'll just generate 0.1 seconds because that'll just create a single layer and it'll be fast. Okay, so go to a top view. We can see that it automatically detected the bounds of that generation box and generated our material right inside of it. So if I went in here and said, well, let's rotate my belt 45 degrees and incline it by 15. Now if I go back here, you can see the material is still in its original spot, because when you generate the material, it creates that material based on all the current simulation settings. So anytime you make a change to your geometry or make a change to your clusters or your particle sets, you always have to regenerate the material. This should always basically be the last thing you do before you start your simulation. So now if I hit regenerate, it goes ahead and finds that rotation and incline, and it puts that material in the right spot. So we'll go ahead and get rid of that. Generate. Now, if you don't want to generate it in one of these Dropboxes, let's say you have your own custom Dropbox, or you're just generating something else, material for some other simulation, you can set this to custom, and then you can pick your drop shape and your center position and your size. So this blue rectangle that you've seen down here, that's showing you where am I going to generate this material. So by default, the center position is 0, 0, 0. And if you leave the size, the X and Y size blank, it assumes that your size is going to be 1 by 1 meter. If I was to change just this X coordinate to 2, you'll notice that it changed both the X and the Y to make this a 2 by 2. Because what it does, it says, oh, there's only one value here, but obviously this has to have an area, because if it was 2 by 0, there would be no area for this drop. So it assumes that, oh, well, if he just puts in one value, we're going to use the same for both of them. But if I said, say, 2 by 1, or 2 by 0.5, or 0.75 by 3, I can change that drop shape. And I can move it around 0.5, 1.5, and 5. So now we're generating it way up there. And I can change my drop shape. So not only can I do rectangle, I can do a circle. So if I said an outer diameter of 1.5, go to my top view, generate. Now we're generating right inside that circle. But what's nice is you can not only do a circle, but you can do an annulus as well. So if we were trying to simulate the discharge beneath a cone crusher, for example, we could say, well, my outer diameter is 2 and my inner diameter is 1. Now we're going to generate the material right in that ring. So you can see that the shaded area inside these lines, that's where we're generating the material. For any of these shapes, that shaded area is where we're going to generate. Or if I want, I could do an ellipse. And now I'm specifying my X major axis and my Y axis. So 2 wide by 1 tall, or 0.5 by 3, or whatever shape I want. So when you're doing a preset location, like for instance generating on belt 1, I could still do a drop shape that's an ellipse or a circle, but I can't set any of the parameters. So it's just going to generate right inside that box. If I go to an ellipse, it's still going to be a circle because it says, oh, the box is square. So it doesn't really matter. So there's really no point in doing anything but a rectangle if your drop shape, if your location is on one of these auto-generated belts. So the last thing to note about our location is if we're generating on one of these belts, perhaps you recall from one of the geometry tutorials that we can split this Dropbox into two sections. If I want, I could split this directly in half or skew it to one side or the other. And that allows it to generate two separate sets of material in this Dropbox. So if I have a split in here like this, now I go back. Let's go back to our top view. And right there's my dividing line. Now when I regenerate the material, it puts it right in the back. Because what it does is it generates these generation points one at a time, starting at 1, going to 2, 3, 4, 5. And the first one that it finds that is set to belt 1, it's going to generate it right in the back there. And then, for example, let's say I had a material set up over here. If I pick 60 to 180, and I say that also goes on belt 1. Now, let's say 0.1. Now that one's going to get generated in the front. So you can see that as I switch between my generation points, it only shows the particles for that generation point. And a handy way, if I wanted to, for example, if I wanted to copy this data right here to generation point 2, I can just go to generation point 1, right click, and I say copy to 2, and it'll copy all these same parameters to number 2. So now when I regenerate, now we've got that same particle set in both boxes. So just a handy way if you wanted to, for example, if you wanted to drop lumps in the back and say fine material in the front, you could do that. Now we've got the big lumps in the back, and then the fines are going to drop on top of that as the material's exiting our Dropbox. Alright, let's get rid of that split. Turn off this generation point 2. So, now the minimum particle gap and the bounding box gap, these are very, very important. The minimum particle gap is one of the most important parameters on this whole page, along with our generation parameters right here. Because this allows us to control how many particles are in each layer so that we can get a good even stream of material going onto the belt. So if I just go ahead and regenerate, what this minimum particle gap is it's saying that each particle, each cluster, has to have at least 25 millimeters of space between it and any adjacent particle. So if I want, I could drop this down to, say, 2 or 1. And when I regenerate now, we're much more closely packed. Or alternatively, I could say, well, let's do 80. Now we've got much sparse distribution in our Dropbox here. So as I mentioned, this minimum particle gap is the primary way that we can control how quickly these layers are dropped. Because when you're generating material by layers, Newton will generate a full layer and then it'll drop it into the simulation. And then based on the amount of volume in that layer, it'll say, okay, when do I need to drop the next layer so that I can maintain this specified tonnage? But if we have too many particles in a single layer, then the next layer that it drops will be so far behind that we're going to end up with gaps on our belt. I'll show you what I mean by that. Let's say my target tonnage was only 300, and I'm going to generate for 10 seconds on belt 1 with a very small particle gap, 0. So when we actually look at this pop-up that keeps coming up, what we're seeing here is total generated, all sets, 1,500 clusters, 6,600 spheres, and 5 total layers of material. And that's between all the generation points. Certainly, since we're only using number 1, this all just applies to number 1. Minimum layer separation, that says how how much vertical distance is there between each layer and the next layer that drops after it. So if I was to drop one layer, if I let this layer drop and keep dropping forever, by the time the next layer is generated right here, the vertical distance between those two layers would be whatever that said, 21 meters, which is really, really a lot of space. You don't need that much space. Ideally, we want this minimum layer separation to be as close to 0 as possible. Because if the minimum layer separation is exactly 0, it means that this particle set dropped and it fell by exactly the width, or by exactly the thickness of the particle set. It fell by exactly that much, and then the next layer was generated. And that means that we're going to have a constant one after the next generating, so we'd have a very even stream of material falling onto the belt. And then finally, our max cluster size, that's just the thickness, vertical thickness of the maximum cluster on any of these layers. So the minimum layer separation, I said we want that to be as close to 0 as possible, but if we get any closer than that, we're going to start overlapping, and we wouldn't want that. So what you should just aim for is try to get your minimum layer separation between 0 and approximately this maximum cluster size, because then we're going to have a really good stream of material, a constant stream. But now with this huge separation, let's see what this looks like when I actually run my simulation. Make sure I've got plenty of time there. Solver run. So we drop a layer. And this is already leaving the simulation by the time we drop the next. And there's this big empty gap, and there's going to continue to be this big empty gap, because obviously for a belt of this size and this speed, the tonnage is just way too small. It's an extreme example, but this shows how we want to get a constant stream of material. So now what if I go in here and I change my minimum particle gap so that we can't fit as many clusters in each layer? Then when it calculates the volume of that layer, it's going to say, well, there's way less particles in this layer, so we need to drop the layers more frequently so that we can still match this specified tonnage. So if we said, say, 100 millimeters, we still got 6 or 7 or 8 times that max cluster size, that layer separation. So let's even squeeze it up more. 150. Now we're getting closer. How about 175? Okay, how about 190? Let's just make it an even 200. Alright, now we're 2/3 of the way between 0 and our max cluster size. That should be good. So now if I go ahead and run this, now look at that nice even stream. We're dropping particles very quickly. Now we have no gaps on our belt. So certainly, as I mentioned, this belt is so wide that having 300 tons per hour at this density is you would never do it. But it's just meant as an example here. So if we change that back to 1,000 and generate, well, now at this tonnage with this minimum particle gap, now we have overlap saying, hey, warning, overlap. So we've still got our same cluster particle layer count, but now before it tells you your distances, it says there's warning, there's overlap on material set 1. Now the max layer overlap, this is basically how far are these layers overlapping. So before we were talking about what's the distance between the separate layers, and now when we're talking about overlap, it basically means that that separation distance is negative, and now our clusters are going to overlap each other when they generate. So this is what happens when that max distance gets less than 0, and we still have our max cluster size. So now if we go ahead and turn down our particle gap to, say, 100, still overlapping, but now we're only overlapping by a little bit. 75. There we go. Now that looks good. So now if I go ahead and run this, again, we've got a good even stream of material. And that looks a little bit more realistic for a belt of this size. So basically, the tonnage, your specified tonnage, and obviously the density, and this particle gap, they all are tied together. And depending on the size of this Dropbox, you got to play with this particle gap so that you get a good layer separation when you're generating in layers. So a different way, rather than changing the minimum particle gap, what else could we do? If I said, well, you know what, for some reason I have to have a minimum particle gap of 150, and that says we have overlap. Well, what else could I do? Certainly, you can't change the tonnage or the bulk density. That's a property of your system. But you could change the size of this Dropbox. So if I go back to my geometry, I can say, well, let's make this Dropbox longer. And by default, that default length is, I believe it's 1.5 times the belt width. So if I said this is 1.8, because that's 1.5 times that, certainly it didn't change. So that is the default. So now if I say 2.4 or 3, we're making that Dropbox longer. Now if I go back here and regenerate, there we go. Wow. Hit it right on the nose. So now we've got at least a minimum separation greater than 0, and I still can maintain this particle gap. But of course, what's the point of doing this? What's the point of having a huge particle gap? Because the entire purpose, the entire reason why our generation method is wonderful is because if I want that minimum particle gap to be 0, Newton is really good at sticking all these clusters in here, leaving as little space as possible. And that's the entire purpose, is doing it this way. I could say, with 0 gap or even with just say 5 millimeter gap, I could say, well, now I can actually shrink this Dropbox. So I could make it, say only 1 meter wide. So it's just going to save a little bit of space in my simulation. There's no reason to have a huge Dropbox with a huge gap when I could just change the size of that auto-generated Dropbox. And now our layer separation is only 0.32. Still a little high, but that would be acceptable though. But in general, based on the size of your belt, the default size of the Dropbox is almost always going to be just fine. Unless you have a really extreme tonnage or a really extremely high or extremely low bulk density, then the Dropbox size might need to be altered. But in general, you'll be able to put this particle gap at a reasonable size so that you can just use that default Dropbox. Then the bounding box gap. That's basically just how much distance do we want between our bounding geometry and the particle set. So if I set this at 100, now you can see that we've got a 100 millimeter gap on all sides here. And that also applies for both the minimum particle gap and the bounding gap apply whether we're generating on a belt or generating in some custom location. So if I had my circle here, and we're still obeying that minimum gap there. We've got a bounding gap, and we've got our let's say I set this at 50. It's going to do the same thing. And what's even nice is, well, let's say I'm doing my annulus. If I say 2 by 1, and I want, let's get rid of the minimum particle gap, but I still want 50 millimeter gap there. It's going to obey that gap on both the outer ring and the inner ring. So I wanted that to be 80 or 100. So certainly, if we go back to our belt 1, and we were talking about modifying the minimum particle gap so that we can, change how much material is dropped in a layer. Let's say 10. Oh, change that back to a rectangle. Well, I suppose rather than modifying the minimum particle gap, we could increase the bounding box gap. If I said 250. Now certainly we have much less material dropped in this layer. But what's the real difference between doing this and simply increasing that minimum particle gap? Because using minimum particle gap, we're gonna distribute that material evenly over the layer, and it's gonna fall on the belt much more in a random and realistic pattern than dropping just a small square. So a real practical application for the bounding box gap is, well, let's say I'm generating material that's really cohesive, really sticky, And if this bounding box gap is 0, then what that means is if I zoom in really close in this bottom corner, the material is actually just barely touching the wall or about to touch the wall of the box. And because of the way the liquid bridge works, actually it would detect that there is supposed to be a liquid bridge between those particles and the side of the Dropbox. So those particles would start out sticking to the side. And certainly they would start falling, but they would fall very slowly and kind of slide along the side of the box. So then when we drop the next layer, well, have these side particles fallen far enough that we're not going to, be generating particles on top of particles? And the answer is, well, that depends on all the parameters. But a way to avoid that is simply say, well, let's just give ourselves a minimum gap of, say 10 millimeters all the time. Because then we won't start out looking at that using that liquid bridge, or even 20. So it's always good to have just some small bounding box gap. Maybe make it half the size of your smallest particle, So let's go back to our generation method, and rather than looking at layer, let's look at the clusters and the particles very quickly, because the whole point here is that it's completely identical to generating in layers, except you just specify a cluster count rather than your generation time. So we can't do the acceleration or the deceleration period here. We simply say, well, maybe I'm using Newton Basic and my cluster limit is 75,000, so I only want to generate that many. And it'll still give me all the same information here. It'll still show me everything I need to see. The point is that now I can do it based on cluster count or particle count. So, how about the block? Let's generate something realistic. Well, let's open up a different geometry here. Where would you actually use this? So if we go ahead and open up a cylinder. So this is one of the default cylinders, one of the default geometries that's included in one of the files. It's also in the Newton demo. And what we would use this for is calculating our solids ratio, which I talk about in a different tutorial. But now when I generate material, certainly the fastest way to do it is not to generate material in layers and drop 1, 1, 1, 1, 1, but simply to drop an entire block. So what I would do is I'd say, well, let's get a top view here, and well, first of all, what's the volume? What's the size of this cylinder? I believe this was a 900 millimeter radius cylinder, and actually I think I save, not in this file, but well, let's just we'll call it 3 meters cubed. Now when I set my location, obviously I want to go to a custom location, because right here I have no more belt. So if I try and say generate, it actually worked. I thought that usually throws in, because I'm on volume. If I say layer, it still works. That's goofy. Must be because I had a belt there previously, but usually it would throw an error and say, there's no belt there, so you can't do that. But, well, let's say our custom location now. Let's go ahead and make this a circle. And obviously what's our outer diameter is 1.2, 1.8, 1.8. And obviously because this geometry is not a perfect circle, we'll make it, say, 1.78, just a little bit smaller. There's my generation area, my minimum particle. Let's give a bounding box gap of 10 millimeters. And now because I'm dropping in a block, we want to raise this up a bit as well. Let's raise it up to there, so that material can drop and impact and have a little bit of distribution. So now because I'm dropping in a block, well, what do I want this minimum particle gap to be? Certainly, if I make this particle gap really big, like 100, and I generate, we're in layer again. Let's go back to block. Now we've got a really tall chunk of material here. What's going to happen now, if I run this simulation, these particles at the top are going to be moving so fast that they're going to slam into this material in the cylinder. They might even move fast enough that they're going to exceed our kill particle velocity, and they'll just be chopped out of the simulation. So we want to turn that gap down. If I turn it down to 10 and regenerate, that looks a lot better. But now you want to be careful as well, because what if I said 0? Now, these particles are all starting very close together, and when I actually drop this block, the particles might not bounce around very significantly at the bottom. So you can imagine if I had generated this at 0.1. If I generated this, maybe 0.15. Go to transparent view. When I drop this material, it's all going to drop right to the bottom and sit exactly how I generated it, and that might not be realistic. So you might want to have just a little bit of a particle gap and enough drop height that the material is all going to shuffle around as it drops into the bottom of the cylinder. I could even, like I'll talk about in the next tutorial, I could even give these clusters a little bit of velocity, random velocities in the x and y direction, so that they'll kind of jumble themselves around as they're falling. But again, with the block, all you're doing is you're specifying the volume, but you can still play with all these shape parameters and all the gaps and whatnot. So I think that covers it for basic generation. The main thing to remember is you're going to be using layer most of the time, and you want to be playing with that minimum particle gap as well as the shape of that drop box. The shape of that Dropbox, although you'll play with the Dropbox shape a lot less than you will need to be modifying that particle gap. So I think that covers everything I wanted to cover for this tutorial. So we'll talk about these other advanced features. Ooh, actually that does not. We want to talk about the output grid. So all this grid is all the input settings. I specify my density, my generation method, my tonnage, all of that. But the output grid will just kind of give me a summary of each of the particles on each of these generation points. So I can see, oh, there's my number of clusters, number of particles, number of layers for this particle set. And there's my maximum cluster height, and this displacement between layers is a huge number because it's all on one single layer, so that is irrelevant here. But if I went back to, let's regenerate this there. So if I'm doing layers and I look at this output grid, now my displacement between layers is actually 0. Not sure why that's 0. Because we only have one layer, that's why. So there's 0 displacement because there's only one layer. Because my tonnage is down to 3 because that's where we were entering our volume. So if I put my tonnage back to 500, we'll generate. Oh, my generation time is 0 as well. We got to change that to say 5 seconds. There we go. Now we can see there's that displacement between layers. And one thing to note is when on my right here, minimum layer separation is 2.85. But right here we're seeing 2.97 because this is basically taking the average displacement between the layers. So it's not the smallest displacement, but in that pop-up menu it was the smallest displacement. And now right here at the bottom I got my specific layer information. For each layer, what time is that layer released, how many clusters, how many spheres in that layer. And I can click through and look at each layer independently. Layer 2, what time is it released and how many clusters? And you can see that it shows me that layer in the rendering window. So I can scroll through each layer, and this is telling you exactly when is that layer dropped, how many clusters, how many particles. So I could go through and just kind of inspect every single layer that's going to be dropped. So the output grid it's just handy for checking each of the different particle sets after you generate them. Alright, so that covers our basic generation, and in the next tutorial we're going to talk about these other advanced features. If you have any other questions, go ahead and see those tutorials or send us an email at info@actek.com. Thanks.